Okay, so welcome, guys. Today we're going to finish up reading chapter 7, and then we'll get back to what we were just talking about, which is building all these builder functions for the parser. So, chapter 7, last time we talked about how to actually interpret expressions, uh, like mathematical expressions. So, chapter 6 described how to parse like mathematical arithmetic expressions. And then chapter 7 describes, once you've parsed them into an AST, how to actually execute them using the tree walk strategy in part 1, which is where you just traverse over the nodes and do the appropriate things at the appropriate times. So the first thing it talked about is how to actually execute the code when it's written correctly. But LOX is a dynamically typed language, so it's possible that you can get things like this, which are which parse fine but are badly typed at runtime. So you need to check things such as when you do a negation, that you're negating a thing that can be negated and not a string. So then there's a section on detecting runtime errors. The way that he's doing it in the book is to reuse Java's detection. So Java also has runtime type checking if you do instance of. So he's just reusing Java's instance of to sort of map it onto the LOX types. And where we left off, he had just gotten through describing all the runtime errors you can have for these operations. And we were here. So that gets us detecting runtime errors deep in the innards of the evaluator. The errors are getting thrown. The next step is to write the code that catches them. For that, we need to wire up the interpreter class into the main LOX class that drives it. So hooking up the interpreter. The visit methods are sort of the guts of the interpreter class, where the real work happens. We need to wrap a skin around them to interface with the rest of the program. The interpreter's public API is simply one method. So interpret an expression. This takes in a syntax tree for an expression and evaluates it. If that succeeds, evaluate returns an object for the result value. Interpret converts that to a string and shows it to the user. To convert a LOX string to a value, we rely on a stringify for a LOX value. And yeah, so then the other point of this is to wrap the entire thing in a try catch, so that when you throw a runtime error, you can print the appropriate message. So stringify, if the object is null, you say nil. It's a number, you turned it into like a string representation, and otherwise you rely on what Java does when you say toString. Okay. This is another one of those pieces of code like isTruthy that crosses the membrane between the user's view of LOX objects and their internal representation in Java. It's pretty straightforward. Since LOX was designed to be familiar to someone coming from Java, things like Booleans look the same in both languages. The two edge cases are nil, which we represent using Java's null, and numbers. LOX uses double precision numbers even for integer values. In that case, they should print without a decimal point. Since Java has both floating point and integer types, it wants you to know which one you're using. It tells you that by adding an explicit 0.0 to integer value doubles. We don't care about that, so we hack it off at the end. Okay. If a runtime error is thrown while evaluating the expression, interpret catches it. This lets us report the error to the user and then gracefully continue. All of our existing error reporting code lives in the LOX class, so we put this method there too. So to print out an error, we error print the message and then where the error was. And we set this bool, who knows what that does yet. We use the token associated with the runtime error to tell the user what line of code was executing when the error occurred. Even better would be to give the user an entire call stack to show how they got to be executing that code, but we don't have function calls yet, so I guess we don't have to worry about it. After showing the error, runtime error sets this field, so had runtime error. That field plays a small but important role. Yeah, so this is at the top level, I suppose. You do a different exit call if there was a runtime error. Okay. Different exit code, I mean. So now that we have an interpreter, the locks class can start using it. All right. So at the top level, we have an interpreter. We make the field static so that successive calls to run inside a REPL session reuse the same interpreter. That doesn't make a difference now, but it will later when the interpreter stores global variables. Those variables should persist throughout the REPL session. Finally, we remove the line of temporary code from the last chapter for printing the syntax tree and replace it with this. We have an entire language pipeline now, scanning, parsing, and execution. Congratulations, you now have your very own arithmetic calculator. As you can see, the interpreter is pretty bare bones, but the interpreter class and the visitor pattern we've set up today form the skeleton that later chapters will stuff full of interesting guts, variables, functions, etc. Right now, the interpreter doesn't do very much, but it's alive. All right, awesome. So, I'll go ahead and read the design note. Some languages like Java are statically typed, which means type errors are detected and reported at compile time before any code is run. Others, like locks, are dynamically typed and defer checking for type errors until runtime right before an operation is attempted. We tend to consider this a black and white choice, but there's actually a continuum between them. It turns out even most statically typed languages do some type checks at runtime. The type system checks most type rules statically, but inserts runtime checks in the generated code for other operations. For example, in Java, the static type system assumes a cast expression will always safely succeed. After you cast some value, you can statically treat it as the destination type and not get any compiles errors. But downcasts can fail, obviously. The only reason the static checker can presume that casts always succeed without violating the language's soundness guarantees is because the cast is checked at runtime and throws an exception on failure. A more subtle example is covariant arrays in Java and C#. The static subtyping rules for arrays allow operations that are not sound. Consider object array stuff equals new integer array of length 1. Stuff at 0 equals something that's not an int. This code compiles without any errors. The first line upcasts the integer array and stores it in a variable of type object array. The second line stores a string in one of its cells. The object array type statically allows that. Strings are objects, but the actual integer array that stuff refers to at runtime should never have a string in it. To avoid that catastrophe, when you store a value in an array, the JVM does a runtime check to make sure it's an allowed type. If not, it throws an array store exception. Java could have avoided the need to check this at runtime by disallowing the cast on the first line. It could make arrays invariant such that an array of integers is not an array of objects. That's statically sound, but it prohibits common and safe patterns of code that only read from arrays. Covariance is safe if you never write to the array. Those patterns were particularly important for usability in Java 1.0 before it supported generics. James Gosling and the other Java designers traded off a little static safety and performance. Those array store checks take time in return for some flexibility. There are few modern statically typed languages that don't make that trade-off somewhere. Even Haskell will let you run code with not exhaustive matches. If you find yourself designing a statically typed language, keep in mind that you can sometimes give users more flexibility without sacrificing too many of the benefits of static safety by deferring some type checks until runtime. On the other hand, a key reason users choose statically typed languages is because of the confidence the language gives them that certain kinds of errors can never occur when their program is run. Defer too many type checks until runtime and you erode that confidence. Okay, so let's see. That did not take very much time at all. So why don't we talk a bit about how this visitor pattern stuff or visiting the nodes in the tree stuff gets turned into Rust. I don't really see a need for us to do visitor pattern. We can just do normal tree traversal, I think.
Visitor pattern might be useful later if we decide to support bigger programs. Normal tree traversal will use stack, and if the stack is too big, but for the example, should be fine.
Okay, so the difference would be just that the visitor is like stores a pointer to where the node, like the node is currently at, instead of using a stack.
Something like that.
All right. So I kind of thought the main benefit of like the visitor pattern stuff that he set up is so that he could do like multiple operations, because he did like one operation for just printing the AST. That's like one way of visiting the nodes, and then another operation for actually executing it. And I don't really
you
care
still
about.
need to specify how to print. In our case, on the expression, we have method like eval. It will do the match on the body. If it's leaf, it will just produce itself. If it's something else, it will do the recursive call. I don't see how you can make it any more simple.
Any more simple than writing a visitor?
No, than making a recursive call.
Yeah. That's kind of what I want to do.
But you were saying, Michael, you were saying that the entire program code, the entire syntax tree of the entire program would have to fit in the stack, or fit in the stack possibly multiple times if it's chopped up.
Not entire, just the path we're taking through it, the longest path.
It's just the stack depth. So we would be limited by Rust's
with one
stack
bigger
depth.
stack, so it's not a huge deal.
Yeah. What is Rust's Rust stack depth?
8 megabyte or 2 megabyte. It depends on the operating system, depends on the thread.
Okay. Okay. So I think it makes sense to go back to this. We could, I guess, go back to the commit where it's like a handwritten parser for expressions and then start doing stuff there. But I think I just kind of want to get the builder functions squared away. So let me make sure. So the case that we're missing to do this is just specifying this, but without a representation function. So I want to try doing that. So I'll keep around the version you had with the representation in case we need to do that. But I think that there should just be a default one, which just returns the token type without doing any transformation on it. Okay. Okay, so rep here is just the expression you want to replace the thing with. Gotcha. So it's not like a function. Okay, gotcha. So in the default case, it's still TT, I think. Right. So now, really, no, doesn't know what. Oh, create token type star. Okay. Okay. Interesting.
We can change the code to how it was previously. If all we capturing is this token type, we just need to try to capture, what is it, identifier, and then substitute that.
Isn't that what I did? I changed it from capturing the representation.
With colonist version, I added. Without colonist version, we had. So it's not, it's ident, but when we prep, it needs to be token type TT on line 309.
I see. Okay. So that's because. Okay, so the token types not being in scope is because of the generated function, not like in here. Okay. Got it. And now it should hopefully tell us where our types are wrong. Looks like we have this like weird. It's expecting a star or something. So here we might have the problem of like the two branches of an OR group aren't the same type. This one has like a bunch of stuff and this one is just one thing.
Yep. So we need to extract and convert.
Right. Okay. So this is so that means we just needed like a separate grammar rule, right? For this like sub thing.
Yep.
Let's see, what would you call this? This is
A member call?
yeah.
No. Expression call dot identifier equal member assign.
All right, does that get rid of that error there? Okay. That does, right? No. Okay. It still thinks we need a star there. Because we didn't just have an empty grouping of parentheses. Yeah, I think so. Okay. Cool. So redundant parentheses don't work, looks like. Like it has to be, the parentheses have to be there for a reason, at least the way we've written it. Okay, let me try to do that to the other ones. So this is interesting because this is the same thing. This is the same thing, but okay. This feels silly. This feels like extra work that we're having to do because of the type system, but all right, so this is a non-recursive unary. Oh, right. Get rid of this. Okay. Is this the only time? There's something here, but we'll see if that goes away once we fix all the calls. So the call has is this the same problem? So primary expression, and then this bunch of stuff maybe. And then, yeah, it's the same thing. So it's either just an identifier or this whole bunch of stuff. So does this even make sense to be another expression case? I think so.
I think so.
All right. Well, I'll just do it. So this is, let's see how this is organized. So primary expression, and then this is like the arguments. And then this is like a You're calling a thing under the primary expression. Okay. So yeah, we'll just make some additional cases. That's not even right.
Why do you have the build call args if you have the build call?
So we're pulling out this piece of the entire thing into a separate rule. And the reason for that is because of the way that the macro works, the every branch of one of these OR groups, like everything separated by a pipe, needs to be the same type. So
Okay.
this is a blob of stuff, and this is a different blob of stuff. They're different types. So that we will get a compiler error. So we're just making them all an expression, and then that means that we have to do some more unpacking of the data to get the original stuff out of the expression, but it will compile. So, and then this other case is I'm going to say field access. So that is just dot identifier. All right. So these things I don't think are the right. That doesn't work. And then this part, I messed it up somehow. I referred to what it was. I think it's that question mark, yeah. Okay. And then we have this problem. So this is where I might want to actually use the representation thing. Except it's not gonna work. Yeah, I might want to make like a separate enum for this, maybe. That all these cases map to.
Well, true, false, nil numbers, true, false, and nil, and they all expression by itself. We can just give a value directly. For numbered string, we need functions to take literals and pack them. Yeah, we have it.
All right. So this thing, yeah, you need like some function, right?
Yeah.
So is that another macro case where the representation is like a function of the original?
Actually, when we have we handling a number and string in macro separately, what do we produce? Are those expressions?
Yeah, those are those special cases? I think they are. Yeah. So they produce
So it should work just as it is. We don't need to do
expression
anything.
number. Okay, great. Okay, awesome. So number, string, identifier, those work. This won't work.
This should work because it's expression.
Okay. I think it's just the empty parentheses. Right? Like what we need is like this kind of thing. Like, what's the representation for this entire thing?
Well, it's expression, and parents are just for grouping. And do we even need
So
that?
does this work? I think that works. Okay, awesome.
And for this, we need to write something. Actually, no, we need.
I think we do.
I think we need to write something.
Okay. Rust Analyzer still doesn't like this for some reason. What's going on? Oh, that's much fewer errors. All right. So it doesn't like the fact that there's a pipe there. Do I actually need this outer parens?
Yes.
Okay, but it just doesn't. Why doesn't it understand that this just means the end of the OR group? It's expecting some other token. You just need to build that in.
With OR group, we expect the parents.
Mm-hmm.
And items inside the parents needs to be token trees, so we need to remember that. So what was it? With 3 members when we had the parents. 552 line left parent expression. So parents are needed here for grouping reasons. Parents including left, right parent.
I thought that's, but it doesn't understand what this means. Yeah, we don't have a case for just parentheses used for grouping. They always have to mean something.
Let's try to explain it.
Sorry. I'll just make that case.
Yep.
All right.
I think it's going to be similar to a repeated group, just without repetitions. Now our group is slightly special.
Yes.
Yeah, this one. We don't need the loop. We call the subtree parser just once. And it should do the right thing.
And then error, we just return that.
I think you can even just push directly into subtree. So results is no longer a vector. We don't push. Yep.
Okay, let me go through this. So initially, we're not doing anything in a loop. So we don't even need.
So we have subtree and we need to push the parse the rest and push subtree into whatever we parsed. Prep. Like, what is it? Line 217, line 218. I think it's very similar to.
So the reason that it's structured like this, where we set results, is because we needed to accumulate results.
Yeah,
but here we don't
run
need
it
to.
several times.
So this goes into like here. So match subtree. If it's good, so the subtree is just the result of doing the stuff in the parentheses. If it's good, then do this. Results doesn't exist. We put that in there. If it's an error, then we bubble it up the same way that we did before. that. So we either get an OK in the OK branch or an error.
Yep.
Okay. Cool. I still need all these parens. Yeah, I do. Okay. Interesting. So it stopped. I need to put this below the other groups that have parentheses, I think.
Yep.
Yep. Okay. That was it. So where's this? Where's the error still? Oh, okay. Cool. So the last thing is duplicate definitions for function. Where is that coming from? I guess which invocation? It comes from function, the grammar rule for building a function. All right. I noticed you had this commented out, I think.
Do we have? Yeah, I added function below just to have it
Oh, okay.
happy as far as step checking goes.
Okay, cool. So that was actually preventing it from finding a bunch of other stuff that was wrong. Okay. So now we make all these, we add these new variants, so I have to make the builder functions for it.
Okay, I think I will spend some time on the weekend cleaning it up.
In what way? Like the file structure or like the actual?
File structure. Maybe simplify the macro a bit. And if you're going to push your own changes, please make a merge request so I get notification.
Okay.
When you just push, I don't see anything.
Cool. Okay. Now a lot more red appeared, but I think that let it get through all the macro invocations. Like we fixed all the macro invocations and now it's just giving us regular Rust type errors, which means building the builder functions will be easier. Yeah.
I've got to say, I'm still astonished at the capabilities of the whatever you call it, Rust Analyzer, the integration between you editing and it sort of pre-compiling, or I don't know what it's doing in the background to throw a red underline on something. But the amount of computation that it's doing to do that seems amazing to me.
Yeah. So, I mean, as you get to larger projects, it definitely, that can add up, that computation.
Do you know what it's doing in the background? Is it literally running the Rust compiler in the background, or does it have like bits and pieces of the Rust compiler slurped into an extension? to something?
It runs Clippy in the background, Clippy or cargo check to check, but it also contains a bunch of its own logic to do the type check, to track the types and where identifiers belong. Because a Rust compiler can complain that this function is not correct, I won't do anything. Rust Analyzer does its best to analyze what it can and to preserve the results between broken states.
Wow. Well, I find it amazing.
Okay. So this is, yeah, I'm just going to say fix macro invocations. Expansion errors, not type errors. Builders. All right. Cool. So that seems good. Well, there's a little bit of work needs to be done here. But yeah, I think we can continue this thing of so yeah, after we're done with these, I say that we should do sort of figure out how to do what the book does for expressions, like interpreting the arithmetic expressions, and then not try to interpret all the other expressions, because it seems like the book's going to have future chapters that are about that. So it's kind of like, I want to constrain the scope of the code we write to what the book describes, until we get to like the end of the entire section, and then we're like, okay, the book's told us everything about how to write this first interpreter, so we can finish it ourselves. All right, cool. We'll stop recording and stuff.